Hi students, in this video module we are going to discuss about time independent Schrodinger equation. In the previous module we learned about time dependent Schrodinger equation. In many situations we know that potential energy of a system does not depend on time explicitly. Instead it varies only with coordinate. So we derived the Schrodinger equation for functions having the potential energy depends on time and position coordinate. But there are situations in which potential energy of a system does not depend on time. Instead, that varies only with the coordinate or the position coordinate. So in such situations, we can simplify Schrodinger equation by removing all reference to the time variable that we used in the case of time dependent Schrodinger equation. Okay, so in situations where potential energy is a function of position coordinate only, in such situations we can simplify the Schrodinger equation with reference to or considering the position coordinate only, or we can disregard the time factor from that. So for doing this we have to write the wave function of the system into two separate sets, one including the position coordinate, another including the time coordinate. As you can see here, the total wave function can be split into two. One is for wave function representing or depending on position, another one a function depending on time. That is, psi of rt can be written as phi of r, that is a position dependent wave function, and t of t which depends on time. We already learned the time dependent Schrodinger equation in 3 dimensions. That is, IH cut dou psi by dou t is equal to minus h cut square del square divided by 2m plus v psi of rt. This is the time dependent Schrodinger equation we learned. In that you can see the derivation for this time dependent Schrodinger equation was uploaded earlier. You can refer to that. Okay, so we used the time dependent Schrodinger equation here now. That is, I h cut dou by dou t of psi equal to negative h cut square del square by 2m plus v times psi of rt. This psi of rt is a total wave function that depends on r. R is position and t is time. But in the above equation, we divided, or we wrote the wave function in two steps. That is, one considering the, or one depending on position coordinate and the other one depending on the time coordinate. So here we are going to discuss about time independent Schrodinger equation. Okay, so in this equation that we wrote now, the time dependent Schrodinger equation, what we are going to do is we are substituting the expression for wave function. What is the expression for wave function here? Okay, so what we are going to substitute here is this psi of rt into this equation. So what will be there? This can be replaced by phi and t. Then we are dividing that with phi of r and t of t. So what you will get is I h cut divided by phi of r t of t. This time we divided both sides of that above equation with the phi of r times t of t. Then instead inside the differentiation it is d by dt of, instead of psi of rt we can write phi of r t of t or by dt. But here we know that it is a function of t. Tau is a function. So phi of r can be taken outside. So I h cut phi of r t of t. Then phi can be taken outside from the differentiation. Then it will be d by dt of, no need for partial differentiation now. Okay. So phi cancels. So what is remaining is I h cut divided by t of t dt divided by dt. That is the left hand side of this equation. Okay. Now come to the right side. There is nothing much to. So here this phi of psi is replaced by phi and t. Okay, and then we are dividing with the phi and t. So the time. So the right hand side also we can substitute the terms. So on substituting that instead of psi, we can substitute phi of r times t of t. So time factor cancels, and what is remaining is the term that we can see here. Now the left hand side is a function of time only. We can see that the left hand side is a function of time, and we can see that the right hand side is a function of position coordinate. So left side is a time depending part and the other one is a position depending part. So this equation is valid only if these two are equal to some constant E, say E. So we can write IH cut dt by dt is equal to E times T. That is by equating the left side with E. Similarly, equating the right side of the above equation with E, we get negative h cut square by 2 mu del square plus V psi of r equal to E phi. The phi from the numerator, sorry, the denominator is taken to the other side. So that is why this expression is given. Okay. So here we got two set of equations, one in time variable and another one in position variable. So from the equation including time, we can see that the value or E represents the total energy of the particle, and the next equation, that is this equation, it is the time independent form of Schrodinger equation. So from the equation 62 that is shown here, we can see that E represents the total energy of the system, of the particle, and the next equation or this equation, it is the time independent form of Schrodinger equation. Now integrating the time dependent part 62, we get the value of time, the solution of the above equation, as t of t equal to e to the power, we can, that is after simplifying that, we get the value of t is equal to e to the power negative I e iet by h cut. So we already know that the psi value is a function of, or psi value can be written as phi of t and t of phi of r t of r. This was the starting split up that we did. Wave function is divided into a coordinate depending function and a time depending function. Here the value of t is now obtained after integrating the equation 62 as t of t is equal to this one. Now that wave function we can write like this, that is phi of r time, instead of t of t we can write e to the power I e t divided by h cut. So we started up with psi equal to phi times t. One is a coordinate depending part, another is a time depending part. The time depending part is the solution for that one, that is T of t is given or obtained by integrating the expression 62 here. Okay, so that is why this is what we wrote here. Psi of r can now be written as phi of r is phi of r times e of negative I e t by h cut. Okay, now again back to the expression number 63, that is a time independent Schrodinger equation. The term inside the bracket, the term inside the bracket can be represented as EH, which is known as Hamiltonian operator, negative h cut square by 2 mu to m del square plus v, that is h. So we can write that expression as h phi equal to e phi. This is the time independent part or time independent Schrodinger equation. Okay, so here Hamiltonian operator h is given by negative h cut square by del square by 2 mu plus v, and E is the energy value for that. Okay, so this is the time independent Schrodinger equation. Now, so we derived the time independent Schrodinger equation by considering the wave function as a set of two functions. One depends on time, another one depends on position. So this type of a wave equation is possible only when the potential energy of the particle is depends purely on coordinate. For all other system, that is, but if the potential energy is a function of coordinate and time, we have to use the time dependent Schrodinger equation. So for special case of particles having potential energy that depends on coordinate only, we can use time independent Schrodinger equation that we derived. Now we are going to learn about bound state problems. What is actually meant by bound state? When a particle is confined to a finite region of space, we refer it as a bound particle. Anything that is confined, if you consider a solid, it has got a definite shape. So the particle inside that solid cannot move out of that boundary. Solid has a boundary, right? So it cannot move out of that. So that can be considered as a bound system. So what is a bound system? Whenever a particle or the particles of the system is confined within a finite region of space, such a system is known as a bound system. Any solid, for instance, is a bound system of many atoms, and an atom is a bound system of electrons and nucleus. So a general feature of any bound particle system is that the wave function of the particle vanishes as we go far from the region where it is confined. So if you consider a bound system, for example, if you consider some solid material, then the wave function vanishes when you move out of the boundary. What is actually the meaning of wave function? Wave function shows the probability of finding the particle. So if it is a bound system, the probability ends within the system itself. We move out of the system, then we cannot see the particle. So the wave function vanishes as soon as we move out of the boundary of the system. Okay. So the reason for this feature is that the probability of finding the particle far from the bound region is negligibly small. A bound particle is allowed to have only discrete values of energy. So now we are going to discuss about an example for a bound state problem in which a particle is confined within a specific region of space and the wave function exists only inside that system, and the wave function vanishes as soon as we move out of the system because there is no chance of finding the particle outside the system. As an example of a bound state problem, we are considering a particle that is confined in a box of potential. So you can see that here the potential energy of the system is 0 within the box, and you can see On the boundary of the system, the potential energy increases to infinity. So that is why we are considering here there is a particle which is inside this box, a potential box there, where the on the boundary the potential is infinity. Inside the boundary the potential is zero. So the motion of the particle is confined to the box because the potential energy is infinity at the walls. It cannot cross the walls because of this high potential energy there. It can move inside the box. So consider this particle, let it be of mass m, and it is having an energy E. So now we can write the Schrodinger equation. We can write the Schrodinger equation d square by dx square of phi plus 2m divided by h cut square e psi, e phi equal to 0. D square phi by dx square plus 2m by h cut square e phi equal to 0. The time independent Schrodinger equation, where phi is the function of coordinate only, or we can say that it is the solution of the time independent Schrodinger equation that we wrote. What is that? D square phi by dx square plus e phi is equal to 0. The solution for that is phi. So phi is the solution for that wave function, the time independent wave function. Now here we know that the potential energy is 0 inside the box. So the energy is purely kinetic. What is the expression for kinetic energy? We can write the expression for energy as half mv square. I divided with m and multiplied with m, then this become m square v square by m, or you can write it as p square divided by 2m. That is the kinetic energy, because energy, total energy is always E, is kinetic energy plus potential energy, but here inside the box the potential energy is considered 0. Therefore the total energy is purely kinetic, and the kinetic energy expression is half mv square. We divided with m and multiplied with m, we get this expression, or p square by 2m. Now this we can write as 1 divided by 2m. I can write this p as, p is the momentum. Momentum p is h divided by lambda. The de Broglie concept of matter waves. P is h by lambda. I can multiply and divide with the 2 pi. So h divided by 2 pi and 2 pi divided by lambda. What is h divided by 2 pi? That is h cut. And what is 2 pi by lambda? It is k, the wave vector. So that is why this expression for total energy become h cut square k square divided by 2m. Now using this, E is equal to h cut square k square by 2m. So rearranging, we get k square equal to 2me divided by h cut square. Substitute this in the time independent Schrodinger equation, d square phi by dx square plus 2m by h cut square e phi equal to 0. In that expression we are going to substitute 2me by h cut square is going to be replaced by k square. So hence we get this expression, d square phi by dx square plus k square phi equal to 0. Okay, k is the wave vector as we defined already, wave vector of the particle inside the box. So the solution for this, what is the solution for this? We already stated the solution is phi. This is the equation, and the solution for that equation is phi. Okay, so phi can be expressed as a sin kx plus b cos kx. Okay, this is an expression, similar expression for the time dependent independent Schrodinger equation, d square phi by dx square plus k square phi equal to 0, and the solution for that is phi, and the phi can be written as a sin kx plus b cos kx, a combination of two sine functions or cosine functions. But we have to find the values of the coefficients a and b. How to find the values of a and b? For that, we can use the boundary conditions. What is actually mean by the boundary condition here? What we considered is a particle in a box, right? The box has got two boundaries. One is the starting boundary, which is at x equal to 0, and then another one is the final position, x equal to L. Okay, so these are the boundary. So what is the possibilities at the boundary? So we have to apply that. That is known as boundary conditions. Okay, so the expression phi equal to a sin kx plus b cos kx. Now applying the boundary conditions as we discussed now. What are they? X equal to 0. At x equal to 0, what is the potential? It is, and x equal to L. These are the values. So at x equal to 0, the wave function, the value of the wave function is 0, or the wave function vanishes beyond this. The wave function vanishes beyond this also. The wave function is confined only inside the box. So x equal to 0, phi is equal to 0. And at x equal to L, there also the wave function is 0. Okay? So applying the boundary condition, we know that the wave function or the particle is confined in the box only, and therefore the what is actually wave function, that represents the probability of finding the particle. Though, so the finding the particle is also inside the box. So x equal to 0, but beyond that point there is no chance of finding the particle. X equal to L, after that also no chance of finding the particle. So that is why phi equal to 0 at x equal to 0 and phi equal to 0 at x equal to L, at these two positions. Now apply the first boundary condition. When you apply the first boundary condition, this equation, what is that? Phi equal to a sin kx plus b cos kx. What is the first boundary condition? 0 equal to a sin 0x plus b cos 0x. Sin 0, we know sin 0 is already 0. That is gone. Then b cos 0, that is 0 equal to 0 plus b. Cos 0 is 1, so b into 1. So this gives the answer for b as 0. Once again, applying the first boundary condition. The first boundary condition is that on the first boundary, that is x equal to 0, the wave function psi is equal to 0. I mean phi. The wave function phi is equal to 0. So applying that in this equation, 0 equal to a sin 0 plus b cos 0. Sin 0 is 0 and cos 0 is 1. Therefore, b, the value of b equal to 0. So we got the value of b equal to 0 from that. Now applying the next boundary condition. What is the next boundary condition? At x equal to L, phi is equal to 0. So we are going to apply that. So 0 equal to a sin k L, because x is L, right? Plus b cos kx. No need to write that again, because we already determined the value of b as 0. So that is 0. So this gives a sin kl equal to 0. But here that this equation a, we cannot put a equal to 0 there. That will not be suitable, or it's a trivial solution. It will lead to 0 by. So now only possibility for this is sin kl equal to 0. So sin kl equal to 0. So what are the possible values of kl? KL means it is the angle theta. Sin theta is equal to 0. So the possibilities of theta are 0, 180, like that, or 0 to pi, the multiples of pi, right? 2 pi, 3 pi, etc. So k equal to n pi divided by L. So that from that second boundary condition, we get the value of k as n pi divided by L. So now using all these values, the solution for the time independent Schrodinger equation phi equal to a sin kx plus b cos kx, we are going to substitute. So substituting b equal to 0, the second term vanishes. What is remaining is phi n, the n, phi n equal to a sin kx, but k can be replaced by n pi by L times x. So phi equal to a sin n pi by L times x. So using this, we can write the expression for energy. What is the expression for energy? We already wrote energy is equal to h cut square k square by 2m. The value of k is n pi by L now, the bound state condition. So h cut square by 2m. Instead of k square, we can write n square pi square by L square. So this equation says that the energy values of the particle are quantized in the box and are decided by the size of the box. So for each value of n, there is an energy eigenvalue, and the corresponding eigenfunction is given by the expression that we learned. That is, phi is equal to a sine n pi by L times x. You can see the wave function that is confined inside the box. When you put n equal to 1, then the wave function is represented by this one. Here you can see. And n equal to 2, this is like we learned the formation of standing waves in the case of when you learned about waves, the same way. So when n equal to 1, this is the wave function, variation of the wave function that is shown here. Okay, now let us determine the value of a from the normalization condition. What is the normalization condition? Integral this is the normalization condition. Integral psi star psi d psi is equal to 0. So here we know that the value of phi is, what is the value of phi? A sine n pi x by L. Substituted that. So phi star phi. So that is a square sine square. This is square value. So integral 0 to L a square sine square n pi x by L times dx. That's equal to 1. This is the normalization condition. So integrating this, how to integrate? See this integration step. A square integral 0 to L sine square n pi x by L dx. We can simplify using a trigonometric identity. Sine square theta can be written as or 2 sine square theta is equal to 1 minus cos 2 theta. So used that equation here, and then integrated the first term dx integrated, we get x from within the limit 0 to L. Next is cos theta is minus sine theta within the limit 0 to L. So this term will vanish. You can substitute the limits, it will vanish. So what is remaining is a square L by 2 only. Okay, so a square L by 2. Now you can equate this to 1, and you will get the value of L equal to 2 divided by a square. No, a equal to 2 divided by L under root. Okay, so yeah, a is equal to 2 divided by L under root. So we got the value of a. Using that value in the expression for the solution of the wave function phi, we already calculated the value of phi as a sine n pi by L times x. In that we are going to substitute a. So it will become root 2 divided by L sine n pi by L times x. Okay. So this is the value of solution for the wave function phi. Now if we include the time dependent part, if we include the time dependent part also. So what is the time dependent part? We already added the time dependent part there. That is psi is equal to actually phi times t. So here we can the value of t is e to the power minus I e t by h cut. This we derived earlier. So substituting that here, we can see this is the time dependent part, and this is the time independent part that we derived now. Okay, so this is the total probability psi equal to the time independent part phi and the time dependent part t. So the total probability density can be written as psi square, that's equal to sine square n pi by L times x. So with again we can see that this is independent of time, so that the wave functions are stationary states, standing waves that we represented in the figure already shown there. So wave functions are stationary. They are stationary waves within the walls of the box. Okay, so